right, so I'm here today to talk about two things, which is machine learning and big data, basically like the biggest buzzword of the last 3 years or 5 years in investing. The angle of my presentation today would be slightly different. Right? We had a lot of materials, a very good presentation today and panel. The angle that I chose, actually, is just to rewind a little bit a couple of years ago when we were hearing so many myths about application of machine learning, right? So a myth is something it's not true, but people, as much as they're hearing it, they tend to believe it, all right? So basically, well, I asked myself how strange it is, right? Finance has a long tendency to embrace new things in order to make money, right? So, and machine learning and big data seems to be like interesting, innovative, right? So what was the cause? What was like at least one reason to explain that there's been so many wrong way of promoting machine learning and big data in finance, so many myths around floating around in conferences, right? So I asked myself, is it something new? Because most of the time, the two main human, let's say, reflexes for new things would be fear and denial, right? But here, machine learning is not really new, right? It's here for a long, long time. As a matter of fact, it's surrounding us in all our applications, in our phone, in our day-to-day. So I tried to find out what might be a reason. So I started with a slightly more fun introduction about that. Does anybody in the audience has idea who this man is? Nobody, all right. This is Galileo, perfect. So Galileo is the father, one of the fathers of modern science, all right? How to make science. So the SD, basically, I'm not going to go into detail for the sake of time, right? Is to come up with a way of doing science, a way of validating research, right? It's coming up with a theory to do prediction. All right, I'm thinking that it's going to be X on Y, right? The impact is going to be that, which is the prediction. After that, doing an experiment, a proper experiment, to verify or not the theory. And this is the way we've been used to make science ever since, pretty much. The thing which is funny is that when we look at how we do science with machine learning, this is the exact opposite. We don't have a theory, we just take data. Remember, data is the new currency. We do a training, we train a model. After that, well, we made prediction, sure. And we do observe, try to make sense or make sense, the prediction and the model that we built. And that's maybe one explanation of how people did react about a new way of doing research, right? Moving on, is in our world, the financial world, we do rely on econometry. Econometry, stats, let's say, basically it's the way of we doing research, especially in Quant. I strongly encourage you to read this paper, which is amazing, and I'm shocked that it's not been quoted more often than that, which is making an extremely good point about how can we classify econometry and machine learning, right? So econometry, it's about unbiasedness, right? Finding estimators that are not biased, right? Machine learning is about making good prediction out of sample. So basically, if you put that back in a bias versus variance space, in econometry, you want to minimize as much bias as possible, even if you do have high level of variance. So poor prediction out of sample. In machine learning, you gladly give away some bias to reduce your variance. So machine learning is a new way of doing research. It's not new. It's a little bit against our old habits, and in finance, especially about asset pricing. And now, the moment we are seeing something which is emerging, which is called this empirical asset pricing. Right? So in my presentation, I want to review some of those myths, all right? In order like to cast them away for good. To do so, I took the case study using US stocks, and we're going to review them. As you can see, the first one is, I'm sure that you heard it before. is that machine learning is only useful for high frequency. So to do so, we're going to train different models with different targets. We try to predict a stock's return for a week ahead, a month ahead, 6 months ahead, a year ahead. The second one is maybe the one that I hate the most. The machine learning is a black box, okay? And the third one, in order to rely a little bit with our host today, is NLP sentiment is only useful for high frequency. So basically the protocol, all right, so we're going to predict different time horizon. We're going to do a classification using boosted trees. All right, the full data set is from 98 to 2018. We're going to split it between training, test, and validation. Absolutely nothing fancy, very boring. After that, we create a signal out of those like different horizons that we're going to predict. We create quintile portfolio, and we look at the returns. All right? This is how a data set looks like for those of you that want some kind of a recap of machine learning for finance, right? Every row is what we called an instance, okay? A stock at a date. Every column is what we call a feature, a score, a signal, characteristics, all right? You see the different types of signals and metrics that we construct, right? About hundreds, fundamentals trading, price, volume, liquidity, absolutely like basic things, right? The things that you are reading in each of the paper. Oh, myth one, okay. Is machine learning more useful in higher frequency? So if this thing is right, it implies two things, right? It implies that I cannot train a model on different time horizons with the same data sets, and it implies that the results will be poor or potentially better for high frequency than the long term. So basically, it will be confronting the results for a week ahead prediction to a year ahead prediction. So let's look at the training of the model. So we're using cross-validation. I don't want to bore you with that. So you see it from the left to the right, you get the different model that we are training. From the left, you get the week ahead training, a month, 6 months, and a year. Basically, when you look at the picture, you see the error on the y-axis. Right? They're displaying decent convergence, let's say. All right? On the x-axis, it's a number of iterations, so the number of rounds, because we are doing a tree-boosted things. Okay? And you're looking at the errors. All right? The level of error seems to be higher for the shorter signal, the 1 week, seems to be better for the year ahead. But at least we can all tell that it's manageable, right? We can train different models for different time horizon. After that, most of the time in machine learning, we do look at quality of metrics, all right? To what extent the model is exhibiting a good quality. Using accuracy, precision, recall, whatever. You've got F1, you've got a lot of tests. For the sake of brevity, I've just chosen 2 here, all right? Remember that we do not suffer for imbalanced classes here because we're just doing a classification model, which is outperforming, underperforming, all right? The whole data sample at each point will be divided in 2. And here you look at the numbers, which are out of samples, quality metrics, accuracy, and precision. And again, well, looks like it's easier, at least it's giving better results in terms of accuracy, to forecast long-term, a year ahead. The question is, okay, fine, it's cute, right? But what are the results? Is it making sense? If it's making sense, you should prove it in terms of portfolio afterwards. And you do look now at these slides. As a quant, we do love to check for monotonic patterns on the signals, okay? And here we did construct some quintiles portfolio, and we're just looking how monotonic the signal is, right? I do imply that by Q5 should be higher or better, having better results and performance than Q1, which is exactly the case. And I'm pretty sure that you are sharing the same impression. It's very difficult to say or to see which one is the best in terms of performance. They do all look the same, but I can guarantee they're not the same. It's not a problem in the presentation, right? So, okay, the question is, all right, maybe on a shorter term, you do have a lot of turnover, or maybe if you do put the costs incorporate the cost in the results, you will see something different. You will see that potentially shorter term will be more effective, right? So take a look here. You've got two sets of bars. The orange one is the Sharpe ratio net basis, so take into account the trading costs using a TCM model. And the other one is the blue one is the growth. As you can see, all the quintile Sharpe ratio on the blue bars are pretty much all the same. This is the result that we saw on the previous slide. And when you look on the orange one, well, it changes, right? You see that here, the one which is highlighted, it's the 1 week ahead. Obviously, the 1 week signal is exhibiting a high level of turnover, which is reflecting in lower performance. And on a net basis, it looks like 1 month, 6 months, 12 months are showing the same results. Again, this is a use case. This is just an example, but still a relevant example. If we move forward, for the sake of time, there is the second myth. The second myth is a very classic one, is that machine learning is a black box. And the funny thing is, you think about that, most of the criticism that machine learning for finance is suffering today are exactly the same as 10 years ago about quant strategies, right? I've been a quant for the last 16 years. More than 10 years ago, everybody was saying, oh, yeah, okay, this is the optimization, it's a black box, right? So it's, oh, no, it's not working for mid-frequency. That's the same criticism, okay? All right, moving on. So the black box myth is a very interesting one because it relies to a new corpus of research that have emerged in computer science as well, because there had been a lot of debate for them as well, right? Outside of the financial debate, which relies to interpretability, okay? Is it important to interpret a model or not? Especially when you're doing deep learning, very, very deep net, is it important to understand why the results are good, all right? So there's been like two groups of people saying that, oh, we don't care as long as the results are good. And the other one say, yeah, maybe, I don't know, take the example of diagnosing a cancer on lungs, right? Might be interesting to check how to interpret the model in order to be sure that it's using the right features. In finance, well, there's less at stake, obviously, but still it's important for us. And you have two types of models. You have what we call global interpretable models, which are interpretability is embedded in them. Anything which is tree-based, basically, is extremely white against to black, right? You can see all the rule-based, and you've got an example here, okay? This is an example of how to predict, I don't know, like a month ahead. This is a third example with some metrics. And basically, it's always the same thing. I won't be boring you a lot. It's just like a rule base. If it's superior to X, superior to momentum 6 months, and after that, you've got a potential returns with the number of occurrences expressed as a frequency here, right? So 3% of the case, you will have a return of 36 if the momentum is superior to 74 and superior to 98. Plain, simple, okay? But you can tell, all right, this is only for tree. What about neural nets? What about like deep learning? I saw that in a previous panel, there's been a question about, is deep learning, can we use deep learning in finance, right? The obvious answer is yes, obviously. All right. Second thing which is interesting in the local interpretable model is what we call feature importance, right? To what extent, when you're building a model on top of instances and features, remember features is signals, characteristics, what are the key features, okay? So it's going to tell you the ones that are the most important. The funny thing here, if you look, I don't know if it's big enough, you can see that on the left side you've got the short-term signal, on the extreme right side you've got the 1 year ahead signals. And the thing that we can see looking at the top contributors for each of the models is that obviously on the short-term signals, price momentum, anything which is short-term momentum, is more important, right? So for me, at this stage, looks extremely white, extremely easy to understand. But it's true that you can make a comment. You could have made a comment, say, all right, it's telling me that it's important, but what about the sign? Is it positive? Is it negative? If you think as a beta, as an exposure, okay? Guess what? There are also models to do that. And those models will be called local agnostic models. And the good things about those models is they can be applied to any machine learning models. I repeat, to any machine learning models. Deep learning, tree boosted, SVM, take a pick. You can use them, right? And the idea of those models is using something which is Shapley value, basically based on the Nobel Prize, relying a little bit on game theory here, is that you will do all the cases and do the contribution for each instances at each time. And the idea is that the whole model becomes additive. So if you want to look at the interpretability, so the exposure of your prediction on a rolling basis, you can do it. If you just want to pick a stock and looking at the prediction split for one stock, you can do it. Everything is additive, okay? And it gives you this very nice and fancy chart, which is called like a shape plot, which is, by the way, a package that you can find in R or Python, whatever, or Julia or Java. It's the same. And it's giving you exactly the same plot as before, but this time is clustering all the instances together in order to see the error bars, to what extent there is a natural bias, and on top of that, the exposure, if it's negative or if it's positive. And that's the whole thing. So if you think about MIF2, right, now with those local agnostic models, we cannot say anymore that machine learning is a black box. Finally, another myth, which is obviously, I'm sure the people from Ravenpack would be sensitive to that, is that NLP signals, let's say like sentiments, is only useful for high frequency, right? You're trading only like the second derivative, the surprises, but you cannot use that in, let's say, a mid to long-term models, or you cannot use that as a blended composite signal with other multi-factor characteristics that you could have. And here, well, basically, we did the same thing. So some of you that are clients from Ravenpack can recognize the database. So the idea is we took the same data set as before, but this time that was composed to trading data, price data, and so on and so forth. But this time we created new features that we added. So the full data set would be 120 features. And we added 20 features based on Ravenpack database, on US equities, different transformation. By transformation, I'm thinking about second derivative, slopes, deltas, average, smoothing, take a pick, different topic. For those of you that are aware of the Ravenpack database, I mean, you can have some kind of group filtering things, different relevance and novelty levels, in order to have at least a full spectrum, in a very agnostic way. Remember, it's the opposite of the Galilean approach. Is I want to have a lot of data, and I want to make sense from those data and to find out what is the inner function behind it. So we did train the model again, and we look at the very simple results. Okay, same thing, which is accuracy and precision, but this time by including those new sentiment metrics. And, well, it does have a conclusion, which is basically including those 20 different, let's say, signals from NLP signals did improve each of the time horizon for the prediction, right? You see that 1 week, 1 month, 6 months, 12 months, both accuracy and precision have increased on average of something like 80 basis points, which is a lot in machine learning, right? Well, after that, the thing which is also very interesting to look at is, all right, is this increase in terms of the quality of prediction by including those new sentiment signals, is it spread evenly on all the sectors? By that I mean, do you think that news, or those like very agnostic sentiment news signal that we created on top of a Ravenpack database, are they useful in the same way for, I don't know, technology stock, utilities, I don't know, company which is doing water filtering, I don't know, a company which is building tanks or weapons? So here, what we are looking at is the accuracy without the sentiment signal, which is the blue bars. From the left to the right, you see basically like the geeks sector 1's classification from MSCI. And on the orange, you see what is the accuracy for the signals that have been included in a data set. And what we can see here is making a lot of sense. Again, most of the results in machine learning are pure common sense for finance, okay? What we're seeing is that is increasing a lot the accuracy for technology stock. It's absolutely not increasing, it's decreasing, I think, the accuracy for utility stocks, okay? Right? It's also increasing the consumer services. And if you dig into the results, you'll see that the topic like partnership will be extremely useful for increasing the accuracy result for technology. The topic on M&A as well for industrials will be helping a lot. So you can actually find out a lot of things that potentially you already know, you already knew, but here you can produce them and harvest them on a systematic basis. So you see that this myth, again, well, actually, it's not true. Before going into some Q&A session, I hope, a couple of points to recap. Again, this whole thing that I'm presenting to you today it's much more insights. It's not a research paper that we're going to produce, but compilation of things that we wanted to be clear. It's always a good thing to recap them. Some of those may have been hard to kill over the years, and thanks to people like Ravenpack organizing those conferences over the last 3 years, it's changing, that's true, but still. So some concluding remarks. Well, machine learning is absolutely not new. We knew that. But that's true that this is a new way of doing research, if you think about it. It's slightly different for the Galilean approach. We don't come with a theory. We don't want to. Right? We want the data to speak for themselves. Right? Some of the myths actually did slow down the adoption phase, even if I can say that now I'm thinking that we are at the end of the beginning of this buzzword phase, that people are rolling up their sleeves and working on those new innovative approaches. And, well, interpretability is something which is extremely important and will be extremely important in the future, especially in finance, and should be promoted. And again, you had an example here, but you had so many today that prove that even if it's not as pure as a new price factors, NLP sentiment is extremely useful in a systematic environment, especially in machine learning. Thanks for your time.
How do you deal with stocks that were in the train but not test set and vice versa?
You don't have to. The idea when you're training a model is to find the higher structure of the market, right? To find if the stock is exhibiting something which is an acceleration in momentum and increasing in sales growth is interesting, okay? If the stock disappears, it's the behavior, it's the interaction between the features which is important. So if you push the reasoning slightly further, you can say that even if you find a way of slicing the market, the data sets, just to keep the more causal effects, right? To shrink the data set with the best example, right? You have to, right? Even if those stocks were not in a training set. As long as you get a decent representation of the full market, the full cross-section, and the sectors. You don't have any imbalanced classes in terms of sectors, countries, depending on the data sets. All right, is feature importance analysis where alpha can really be found in ML? It's a very good question. I would say the thing differently. If you're skeptical about ML, which I can understand at some point, right? But you're still a quant. And you have you building a multi-factor portfolio, so you've got, 30 to 100 to 200 signals. Nothing is against the fact that you can run some interesting ML models, boosted trees, neural net, and you check what are the most important features, all right? The test that we do like to do in ML for finance in order to validate the fact that we find something interesting is to compare the ML prediction, the final signals, against the linear combination of the most important variable, right? Because there is a two-step, this is a two-step game. When you're doing ML, first it's going to pick up the best predictors, which are the best, the main contributors in terms of features. But after that, this is also blending them together on a nonlinear basis, right? So you have the first step, which is finding the most important features, and the second one, blending them in a nonlinear thing. What you expect for a pure and decent ML model is to do both, okay? So yes, there is some alpha in it.
Susan?
Yeah, have you explored faster horizons? HF management told that machine learning typically works better intraday when you have many more tick data points. 1 week is not HF.
It's on a daily basis, that's true. 1 week is not hedge fund. Well, sorry, high frequency, that's true too. Well, I did not try it on a tick data. I did it on a daily basis. Daily basis, the results are pretty much the same. When I'm presenting something which is 1 week, 1 month, 6 months, 12 months, it's because it's relied much more to the factor investing world, let's say, which I'm coming from. But I agree that, yeah, high frequency would be tick by tick.
Have you explored machine learning performance at higher frequencies than 1 week, say intraday?
No, still the same answer. I did not change it.
How do you assess the risk of overfitting, particularly in fields with limited data sets?
Oh, that's the beauty of it. I mean, that's the whole point of being behind the machine, right? Because if you think about it, all the codes, like all the codes are open source codes, right? That you can find in Python or whatever. So my added value is, first, my domain knowledge as a quant expert. I did experience some drawdowns in the market. I do a little bit know about the market. Second added value is how can I be sure that I'm not overfitting the data? And this is the part where you have to be smart, right? So regularization. So I won't recommend a machine learning algorithm that is not embedding some regularization parameters. So in XGBoost, you had a lot of them. In neural net, there are dropouts, or you can add also like some L1 and L2. And that's the thing, to regularize as much as possible in order to be sure that you find a higher space structure of the market, right? And this is the whole added value of the quant for ML.
We only have 1 minute left, so we'll take one last question.
So last question, how do you deal with stock universe change, new listings, delistings, spin-off?
Same thing. This is a problem which is not related especially to machine learning. This is a quant problem. When you train your model, you make sure that you can spend a lot of time in the data curation part, which is I want to have a universe of stocks that have been always in my all samples, right, from day one to the last day. I never find that it was giving like good results or different results. The only thing that you want to find is what are the metrics, what are the interaction that matters, right? So spin-off, obviously, this is at the level of the creation of the signal or problem. I'm not going to incorporate stocks that have been just, I don't know, like, let's take for instance Uber, right? What's the momentum, long-term momentum of Uber? We have absolutely no idea. So I would just shift the question at a different part of the investment process, which is at the signal construction level, and on top of that, at the universe curation level.
Tony, thank you so much for joining us today. Thank you.
This is Raven Pack.